The next one thing we're going to look at is trig, what we call trig integrals. Okay? Integrals that involve trig functions. So this is all trig functions. Okay, so the first line of defense here is a big part of this is identities. And there, I've given you a list of, so use identities. To change the form, so we're doing whatever we can to change the form into something more workable. And so the identities are crucial. And here's a list that I will post on Blackboard for you. These are the ones that you need to know. So the basic definitions of tangent, cotangent, cosecant, and secant. All the Pythagorean identities. So sine squared plus cosine squared equals 1. And then the equivalent for tangent squared and equivalent for cotangent squared. So this second one just comes from the first one by dividing all terms by cosine squared. So if you take the original Pythagorean identity, divide all the terms by cosine squared, you get that second line. Okay? The third line is dividing everything by what? Sine squared. To get that third line, you take the first line and you divide everything by sine squared. So it's just a variation on, they're all variations on the Pythagorean identity. Okay? The double angle identities, there are 3 different versions for cosine 2x. And then the half angle, as we're going to see, are very important for these. So these are the basic identities that you have to know. And that's going to be a big part of doing these integrals of trig functions. The next thing is just algebra. Okay, so there's going to be algebra. You're going to multiply things out. You're going to just use the distributive property. You might add fractions. So just basic algebra stuff. And then the last thing, many of these involve undoing chain rule. Not all of them, but a lot. So you're constantly on the lookout for undoing the chain rule, or you're trying to manipulate this thing with steps with 1 and 2 to get to a place where you can undo the chain rule. Okay? So these are the main 3 things that you're going to be at play when you're working on these integrals of trig functions. Okay? So let's try some examples here. First one. Integral cosine squared x times tangent squared x. So there's several things we could do here. The question is, what's going to be the most helpful? What is going to help make this easier or possible? So the first thing we can ask right off the bat, is it undoing the chain rule? Right off the bat, is it undoing the chain rule? No, not really. Okay, so remember, undoing the chain rule, we're looking for the chain part, the derivative of the interior function of the other part. Doesn't really fit, okay? So what could we do to make this simpler or manageable or something? So one technique is to get everything in terms of cosine and sine. So we could do that first. We could change this tangent squared to what? Yeah, if tangent is sine over cosine, then tangent squared is sine squared over cosine squared. Helpful? So using the so here I just use an identity. I use the identity for the basic definition of tangent. Was that helpful? Very. Why? Very helpful. Yeah, now we've got this nice ratio, cosine squared over cosine squared is 1, and it goes away. And so now, essentially, what I gave you at the beginning is the same as sine squared. Okay? Is that undoing the chain rule? What else would we need? So what additional thing could you put into this integral so that it would be undoing the chain rule? So how could I include something else so it would be undoing the chain rule? What would it be? Yeah. What's that? Add 1/3? No, not quite. This is the same as sine. So when you see this notation here, sine squared x, that's like taking the sine first and then squaring it. So what else would I need so that it would be the result of a chain rule derivative? Yeah? What's that? Yeah, so if there was also a cosine x included, then that would be undoing the chain rule, right? And our antiderivative would be what? If it was sine squared times cosine, antiderivative, not 1/2. We would do the antiderivative of this sine, so something squared. So it'd be what? 1/3 sine cubed. If there was a cosine in there, it'd be 1/3 sine cubed. We don't have a cosine, all right? So sine squared. Do we have an identity then? Down here, okay? So, this is maybe the most important thing to learn from this section, trig integrals. That sine squared, just the integral of sine squared, you use the half angle formula. This may be the one we see the most all semester. If you have just sine squared or just cosine squared, that's a matter of using the half angle formula because we're home free. We can do it. So sine squared is 1/2. 1 minus cosine 2x. And that's easy to finish. So we just have two terms now. First term is going to be antiderivative. So I think so we could just take the 1/2 out first if we want. Antiderivative of 1. Antiderivative of minus cosine 2x. So minus sine of 2x, half. So you could have this multiplied out, it'd be the same. 1/2 x minus 1/4 sine 2x, that's fine too. Okay, again, probably the most important kind of fact of today's identities lecture is that when you have just sine squared or just cosine squared, to do the antiderivative, use the half angle formula. That's like the #1 thing that shows up the most out of today's lecture through the whole semester. Is that a question back there? Nice and loud. Probably. Did I make a mistake? Shouldn't there be what? I think it's okay. What? Okay. I think it's good. Am I good? Did I do this right? Okay. Questions on that first example? So notice we had everything. We used identity. We used two different identities. We had some algebra cancellation. That's the nature of these. That's what they're like. Okay, next one. So they're going to take some ingenuity on your part. So there's some trial and error, problem solving. I can't do every possible type of every example. But I can kind of give you an idea of what they feel like. Okay, so we got cosine 2x times cosine x. So this is a problem that we have a different argument. Here, my argument for sine is 2x. Here, my argument for cosine is just x. So in terms of if we applying some technique that is taking those together, we can't really do anything because it's a different argument going into sine and cosine. So, for instance, there would be no undoing the chain rule in this because this 2x is different than x. Okay? Those have got to match up if we're going to be able to use something that involves both of them together. Okay? Double angle formula. What is sine 2x the same as? 2 sine x cosine x. Apply the identity. Cosine times cosine is cosine squared. Okay, so now if you've been with me on this journey and you've paid attention, we should be able to do that. You should be able to finish that up. See if you can finish it up. Remember what this means. So if this notation's ever messing you up, just remember that that's what this means. This may help to rewrite it that way. How many people think they have it? Not finished, but you know what to do. You're on the track. You know what's going on. Okay. You should recognize this is a very important thing. You should recognize what's going on here. And what is going on here? What are we looking at? What is it? It's chain rule. You see it's undoing chain. You've got a composite function. Sine x is essentially the derivative of cosine x. There's the chain part, right? There's the chain. So antiderivative is essentially what? We're focusing here and taking the antiderivative, which is 1/3 cosine x cubed. How many people got that before I wrote it up there? How many people? Raise your hand, nice and tall. Okay. A lot, but not enough. You need to start recognizing this, undoing the chain rule. So that we've been working on it. It keeps showing up through this whole unit and then all semester long. It's the most important technique. Probably. No, I'm not done yet. That's just kind of first attempt, right? First attempt. So this is the basic idea of it, that I'm going to do this. But we got some things to clean up, right? What do we need? We need a 2 and also something else, a negative. So, sorry, I didn't mean to imply that was the right answer. That's just the idea, right? The idea of getting started. Yes, we have the 2 and then negative because the derivative of cosine is negative sine x. We don't have a negative. Done. Questions on this one? Okay, something a little more involved. So general forms like this. You'll see these problems. Sine px cosine qx, or tangent or let's do A and B. P and Q is a little weird, but you do A and B. Anyway, so some power of sines, some power of cosines, or some power of tangents, some power of secants. Example. Here's how these work. We are looking to rearrange this so that it is undoing the chain rule. Okay, so we're looking to manipulate this so that we make it undoing the chain rule. And so with any power of tangent would be no problem if we had what over here? Any power of tangent would be easy, undoing the chain rule, if what was over here? Just the derivative of tangent, right? Which is secant squared. What do we have? Secant to the fourth. So I'm gonna grab a secant squared, thinking that if I can get everything else to be in terms of tangent, then I can undo the chain rule because my secant squared is the derivative of tangent. So when I pull out that secant squared, I'm left with secant squared x tangent to the 7th x. What was my goal? Everything in the brackets written in terms of tangent. So can I do it? Can I get everything written as tangent? And what would I do? Yeah, but use the identity Pythagorean. So secant squared, I can make it equal to tangent squared plus 1. Right? Everything inside the brackets is, if it's everything's in terms of tangent, and I've got secant squared, then I can undo the chain rule. So actually, I'm going to do it twice now. Now I've introduced two terms in there, so it's going to be like two antiderivatives. The first one is going to be secant squared times tangent to the what? 9th. And then the other one's going to be secant squared times tangent to the 7th. So I just distributed there. I just distributed kind of both of them. Did you catch it? So I grabbed the secant squared thinking if everything else could be tangent, some power of tangent, then I could undo the chain rule, no problem. I changed that remaining secant squared into tangent squared plus 1. And then I multiplied out, so I got tangent to the 9th, tangent to the 7th. Each of those now times secant squared. You finish, right? You finish. Go for it. Okay, how do we do? First one is, should have this by now. So that would be 1/10 tangent to the 10th. And questions? Are you following what's going on? Does it make sense? So that's on these forms of a high power of sine and cosine multiplied, two powers, or tangent secant. So it also would be cosecant. Cotangent and cosecant would be the same. You usually see tangent and secant more though. We're maneuvering for undoing the chain rule. That's what we're doing. We're maneuvering for undoing the chain rule. Questions on that? Okay, so same idea, but this will be different. So see if anyone can figure out the puzzle here. Similar, but different. There's a big major difference to this one that I'm going to leave it to you to see if you can figure it out. It takes some ingenuity. But it's the same kind of goal, but different. It's different. You're going to have to see if you can figure it out. So you can try exactly what we did in the last one, and you're going to run into a roadblock, so you have to adjust, okay? See how you do. So if you tried this approach, you quickly find it does not work. Integral secant squared and then a bunch of tangents in the brackets. This doesn't work. So you need a different approach. What else could you do besides this? So everyone think about it. Yep. Rather than tangents and the derivative of tangent is secant squared, what another way to do this? So rather than derivative of tangent, pulling out derivative of tangent, what would you do? Pull out derivative of secant. So rather than starting by pulling out derivative of tangent, pull out derivative of secant, and then get everything inside in terms of what? In the brackets would be all what? Secants. Earth to class. Is it getting through? What is derivative of secant? Secant tangent. Which leaves what? Secant to the fourth tangent squared. And now everything in the brackets we need to be in terms of what? We want secants, right? If everything in there is secants, then we can do undoing the chain rule because I've got the chain over here. I've got the little derivative over here of secant. How am I going to get everything over there in terms of secant? How do I, so I got secant to the fourth, that's fine. So I need to get that in terms of secant. What is it? Secant squared minus 1. So I can use the same identity, but now I'm solving for tangent squared. Secant squared minus 1. See what happened? So you have to know your identities, you have to be good at algebra, and you also have to use some ingenuity. There's problem-solving aspects to these, okay? So really in here we've got what? Secant to the sixth and secant to the piece of cake now. Write down the answer. So that times secant tangent, that times secant tangent. Okay, antiderivative. First antiderivative is? Let's just call on someone at random and see how we're doing. How about right there with the green pencil and the gray sweatshirt? Yes, that's you. How do we do? First antiderivative is what? Nice and loud. No, behind. Sorry. White strings, green pencil. That's you. Yep. Okay, so how about here in the gray tank top? Yeah, first antiderivative. I got 1/7 secant x to the 7th. Okay. Other one is right here in the. Yeah, go ahead. 1/5 secant x to the 5th. Power rule on secant, and we've got chain rule. We've got that derivative of secant right there, so we're set. Okay, I can't do every type of example. I don't have time. Like I said, it's going to take some ingenuity on your part in some of these. There's one. I want to address one other thing before we go. Yeah.
Sorry, can you explain
Where it went?
Yeah.
So in order to do the antiderivative of secant to the 6th, I need that as undoing the chain rule. Right? Where did it go? Well, when you undo the chain rule, two things collapse into one, right? So this is the f prime. This is the g prime f. When you do undoing the chain rule, the f prime goes away. It collapses back in. You remember that? Like all of them, right? And then same thing with multiplying that by that. So when you're undoing the chain rule, you basically have g of f. And the f prime is gone because the f prime popped out when you took the derivative, so it pops back in when you take the antiderivative. Oh yeah, plus c, sorry. Okay, I want to just, no, we don't have time.